All right, so here we have a relatively simple circuit, but making it a little more complicated is the fact that the battery that they have has internal resistance, and so we need to try to learn something about this whole circuit, really just from one graph of three data points. And this is a really common type of problem to see on the AP test. So hopefully after some practice you'll have it down. So first, our first step is to learn things about the circuit we have before doing any predictions. Right, so parts A and B are both about that, which is figure out the EMF of the battery and figure out the internal resistance of the battery just from that graph and sort of the sketch. And kind of, as always, a good place to start is to try to describe the circuit mathematically, which is Kirchhoff's laws. And in this case, we have a nice completed loop, and we have information about current and potential difference. So Kirchhoff's laws kind of seem like a good place to start. So if I start with my circuit, right, which I'll draw right here. Right. There, so there we have capital R, little r, and EMF. And so really this whole thing I'm outlining in blue, that's the battery. But I've drawn it as two pieces just because that way it's easier to show the resistance and the EMF parts. And so if I write Kirchhoff's laws, loop law to describe this, actually I should probably add that we have current I flowing through, whatever it might be. We find, right, if I start at the black dot, we have negative I capital R, actually, yeah, right, that's the potential difference across the variable resistor. We have negative I little r, that's the potential difference across the internal resistance, and then we have the EMF of the battery, and that's a complete loop, so that those potential differences all add to be 0. And so when I look at this, we have two things that we want to find, right? Two unknowns. And we don't know a huge amount, but we do have graphical data that tells us something about the current. And so the only thing I don't know capital R, because it's variable, and it's not given in the graph. But if I look a bit more closely, my graph given has something called the potential difference between points x and y. And point x is here, and point y is there. So Vxy, actually, let me change colors. So Vxy is the same as the potential difference across resistor R, which is this whole thing right here. So in some sense, by skipping a step, I overcomplicated it, but I know how I would have approached the problem initially, so that's why I started it that way. So we can plug this kind of in now. So we have the known from the graph, Vxy. We know from the graph I. We want to find little r, and we want to find the EMF. Two unknowns, right? So it doesn't look like we can solve it, but the important bit is that we have multiple data points for both of these. So we can just pick two data points and give ourselves two equations from that, right? So if we pick Vxy is 4 volts, right? Then we've also picked that the current must be 1 amp, and then that, right, times little r plus epsilon, that'll equal 0. That's one equation. But we could also equally write, using the center data point, 3, Vxy is 3. The current then is 3 amps. So 3 times little r plus epsilon equals 0. So we have two equations with two unknowns, right? The blue stuff came from the graph, and the red is our unknowns. We can solve that system of equations, right? That's just algebra at that point. Probably the easiest way to do it is to subtract one equation from the other. That would cancel out the epsilon part. And then you solve for little r and then plug back in. So if you do that algebra carefully, right, I'll set up a little piece of it. So epsilon minus r minus 4. If I subtract the whole other equation, oops, I'll write that a little neater, which is epsilon minus 3r minus 3, a bit neater again. Okay, so if I subtract the equations like that, I'm going to get 0 plus 2r minus 1 equals 0. Right, and that's pretty easy to solve for r at this point, which gives us r is 0.5 ohms. And now I'm going to take this and plug it right into there, and if I do that, I will get epsilon is 4.5 volts. So that's the way that I would approach this problem, to solve both A and B kind of together. There is another way if you're more comfortable with the concepts, and that requires knowing what does the EMF mean. EMF, by definition, is what the current would be, or sorry, what the potential difference across the battery would be when no current flows. So if I go back to my graph, so we have 3 data points right here, roughly. Actually, draw it exactly how they have it. Again, okay. So we have 3 data points, and we know that EMF is what V is when I equals 0. That's the definition of the EMF. So I can just take this graph and say, well, when the current is 0 is right here. So where would that be? It would intersect somewhere back here, right? It's the y-intercept. And you can see what that is on the graph. And so if you just read the y-intercept of this graph, that is, by definition, the EMF, which is very clearly, visibly, 4.5 volts. So great, so we've got that. The resistance is a little bit more complicated, but not a huge amount. Again, we can write Kirchhoff's law, right? So epsilon minus Vxy minus IR equals 0, right? And so if we do that, now we want to try to say, kind of do a graphical analysis again. So this is y, and this is x. So let's rearrange that to make it look like the y equals mx plus b linear equation. Y equals r times I, right, plus Vxy. Okay. Now I flipped a sign, so I've got to get these all the other way. Okay. So there's, now I've got the signs right. Okay, so negative r times I. Okay, and so from this I can identify from the graph, right, y, x, and therefore this is the slope. And so we can measure the slope of that line. We find the slope is negative 0.5, so r is positive 0.5 ohms. Once again, the same answer. Either one of those approaches, as long as you explain them fully, is acceptable. The second one is probably a little bit more useful, but it's also a little bit trickier sometimes to see. And so once you finish those parts, that's, I think, the hard part of the problem. The other parts are sort of just plugging stuff into equations. So on to part C. So we want to figure out the value of the resistance R that produces a current of 3 amps. So we start with Kirchhoff's law again, right? That's clearly what's going to be involved. We know potential differences in currents from the graph. We want to figure out resistance. That's Kirchhoff's law. So epsilon, to produce a current of 3 amps, so we have 3 times little r, right? Minus the same current, 3 times big R, equals 0. Right, that's our general equation to get a 3 amp current, but we just figured out epsilon and R, so we plug them in. 4.5 minus 3 times 0.5 minus 3R equals 0. And that's a really, really easy equation to solve. We can do it. R is 1 ohm. Right? And that's all part C is, right? Recognizing Kirchhoff's law and using the information you found before. The maximum current a battery can produce. So we got to think, what does that mean? Well, we know that the biggest current comes when the resistance is smallest. We can't get rid of the internal resistance, so the way to make the total resistance the smallest is to make capital R as small as possible. In other words, take it out of the circuit. So epsilon minus I times little r minus 0, right? There's no resistor left there, equals 0. 4.5 minus I times 0.5 equals 0. And once again, now it's an easy algebra equation to solve. We find that I equals 9 amps. Right? The key to that one, again, just recognizing the meaning of maximum current. It's when the resistance is as small as you can make it, and you can't take the internal resistance out. And finally, part E is just a circuit diagram, right? How would we measure the current, and how would we measure the potential difference? So we have our battery with the internal resistance. We have our variable resistor. And we want to know, how do we figure out how to attach these things together? So, ammeter. Ammeters measure current, which means the current must flow through it. So it has to be in series. That's really, really sloppy. Right? So ammeter is in series. Voltmeters, since they have to measure a difference between 2 points, they have to be in parallel. So there's a couple different ways where you can attach the voltmeter. I'm going to attach it on this side. You could also have attached it like this. That would be fine. Either one. The key is it has to be in parallel with either the battery and internal resistor, both, or the big resistor, capital R. Either one. And that's all there is to that one. Anything like that.